We are going back today, way back to the very beginning of, well, what became the defining public health crisis of our time. I mean, think back to those first few months of 2020. The world was just starting to grapple with this new virus, SARS-CoV-2, and how fast it was spreading. You had headlines, what, by early March? Over 80,000 cases, 3,000 deaths in China alone, and it was clear this was going global. And the biggest question wasn't just where, but how. How does this thing actually get inside a human cell? So for this deep dive, we're going straight to the source, a foundational paper from that time that mapped the infection's very first step at the atomic level. We want to understand that lock and key mechanism.
Right, and that lock and key idea is really central to this whole family of viruses. We're talking about the beta coronavirus genus. So that includes the original SARS from 2003, MERS, and of course SARS-CoV-2. They all use this massive structure on their surface. It's a homotrimeric spike glycoprotein.
It's like a three-part antenna.
Exactly. And that spike's entire job is to find one specific thing on your cells, the ACE2 receptor, angiotensin-converting enzyme 2. That's the front door.
Okay, let's unpack that. Because if binding to ACE2 is that first critical handshake, then getting a picture of that handshake, I mean, an actual 3D map, that's everything. And these researchers, they did exactly that. They mapped where every single atom touches. Why is that level of detail so crucial? It's not just, for curiosity's sake, right?
Not at all. That map is the bullseye. It's the blueprint you need to design anything to stop it, whether that's a drug to block the lock or an antibody to cover the key. So to get there, they focused on the part of the spike protein that does the actual work. It's called the receptor-binding domain, the RBD.
The RBD.
Yep, it sits on the S1 subunit. And first, they had to prove it. They took HeLa cells, standard lab cells, and the ones that had human ACE2 on their surface could be infected. The ones without it, the virus couldn't get in.
So that confirmed it. ACE2 is the only game in town.
It's the necessary target.
And the method they used to get this map, I mean, this is just classic structural biology. The source says they used X-ray crystallography.
You basically create a crystal of the two proteins locked together, the viral RBD and the human ACE2, and you shoot X-rays at it. The way the X-rays bounce off gives you this incredibly detailed 3D map.
And the detail here was what, 2.45 angstrom?
Yeah, 2.45 N.
Which, for anyone listening, an angstrom is 1/10,000,000th of a meter. So we are literally seeing the positions of individual atoms. That is a fantastic resolution.
It is. And once they had that map for SARS-CoV-2, they could put it right next to the one that already existed for the 2003 SARS-CoV. And this is where it got really fascinating.
What did they find?
They looked almost identical, even though the genes that code for their spike proteins are, less than 80% the same.
Wow.
The whole binding strategy, the way the new virus's RBD grabs onto ACE2, is nearly a mirror image of the old one. The researchers saw this as, well, a classic case of convergent evolution.
Meaning that